So in the previous sessions, we have been discussing regarding Python. So there we were discussing about different types of operations. So where we got these operations from? Because we said that we have different types of data that we call as data types, and each data type they define some operations which are valid on that. Okay, and we have so far covered arithmetic operations, relational operators, and then we have also covered logical operations like and, or, not, etc. So now today, one of my really close to the heart operations that are called the bitwise operators. Bitwise operators. Okay, why are they called bitwise? The first thing is because they operate at bit level. That's why they are called as bitwise operators. Okay, the bigger picture is that we wanted to build a project in which we wanted to manage our personal finances. For that, we learned how to take how to take an input and then how to project the output to the user. And now we have different types of data that we're going to take the input. Let's suppose name, it's a string. So string will have to manipulate in a certain way. We'll take incomes as an input, what income and what different streams of the income, and we'll have to manipulate different things in that. And then probably we'll have to take multiplication, a lot of things have to be done. Okay, so that's the reason we first covered data types, and after that we said what are the operations that are allowed on the data types. Okay, today probably we'll just code these parts which we have covered so far. Now going to again bitwise operators. So it operates on the bit level. So before going to bitwise operators, they are uh, most confused and misinterpreted operators. I have not come across a really good content per se where these have been clearly explained if it is not an advanced book. Okay, so I'll try to make it as simple as possible. So before digging deep, let's start with how do computers represent numbers. This is really important to understand in order to understand the bitwise operators. People usually they start with the bitwise operators, but we don't know underlying how the computers store the integers or store these numbers. Then it becomes a problem. Okay, so let's see that. So there are three ways in which we sort of represent numbers in the computers. Okay, so the first thing is we call that as signed magnitude. Okay, and the second thing is ones complement, and the third is two's complement. This is how we represent these I'll call signed numbers, or different ways to represent signed integers I can write. Okay, these are for the integers, and I told you about floating point numbers, or which you have float or double. There are two standards, that is IEEE 754 standard. One is called as single precision standard, and another is called as double precision standard. So single and double precision. So this is the way computers store numbers, because you know that everything at computers level is binary. It's just bits, ones and zeros. Okay. So now let's see. First, I'll introduce some number systems, so we get some clarity. Okay. Do not lose the goal. I'm just zooming in a bit, and we're basically we are reading about Python. Not even Python, we are basically learning art of programming, and from that we're learning it from a Python's perspective. Now I zoomed out in a bit, that's Python, and then we're learning different data types and different operations on those things. Now before going to the bitwise operations, we need to understand how computers store the numbers. So before that, I just need to tell you what number systems are. Okay, there are different types of number systems. Let's suppose these are usually used for counting or representation. They're just representations. Okay, as you know that computers, they understand either there are two level systems. What we call computers are two level systems. Two level system means that they understand only two things, that is on, off, up, down, high, low, something like that. And now we need to represent this sort of information. Okay, that's why I said number system is nothing but a representation. So as now computers understand just high, low, on, off. Let's suppose computers are made up of transistors. So there they understand current is there or current is not there. If current is there, that means 1. Absence of current means 0. It's a two level system. Let's suppose if you talk about mechanical some computers in which there are mechanical devices. Okay, if you want to make it a two level system, let's suppose we can say two level system can be like this. If something is rotating clockwise, that we can call 1. If it is rotating anti-clockwise, we can call that 0. This is what I mean by two level systems. Okay, they only have two states. Okay, they have two states. Now we need to represent these things. So what we have done is we have introduced the symbols 1 and 0. 1 represents one state and 0 represents other state. Okay, that's what computers understand. Now, in order to count something, let's suppose, in order to count something, let's suppose there is one entity of a thing. So I'll write 1 like this. Okay. Once I have to write 2, now I need more sort of bits I can call, or more place values where I can take these places. Okay. If I represent, let's start with 0. So zeros means nothing. Everything will be like this, zeros and zeros, zeros. Okay. Let's suppose we start with this. This is 0. And then when we have to count 1, or we have to represent first level, so what we'll do is we'll let a 1 like this. Now, if you see that only two possibilities are there with two symbols. So there are only two possibilities, 0 and 1. So let's suppose if I have to represent a system which is in state 3 or something, I need additional placeholders. So that's why I'll call this as 2, 1 and 0. I'll just increase the number of placeholders. Okay, usually in computer science we call them bits. I'll increase the number of bits. Why are they called as bits? Because they are binary digit. Okay, 0 and 1 are called as binary. They're binary digits. I take this bi and I take this t. So this is bit. So one bit is either a 0 or a 1. Okay, I hope everybody is following me. So here we have a two-level system. For the two-level system, we need a representation. So for the representation, what I said is, I'll introduce some symbols, 0 and 1. 0 means a one level and 1 means some other level. So here, so if there is a current, we call it 0, we call it 1. If there is no current, we call it 0 in the modern computers where we have these transistors. Okay, so now I was saying if you have to represent 0, you can represent like this. If you have to represent 1, you can represent like this. Now in order to represent 2, for that, we'll just increase these placeholders. Number of placeholders are 1 and 2. Now increase this. And now we have 2 placeholders. That's we have 2 bits. So now there are more possible. If I have to write now 3, so how I'll write 3? 3 will be like this. Again, if I have to write 4, let's suppose, again I'll increase the number of bits. Now I have to give some structure. Okay, in order to do that, I have to give some structure. Everybody is they understand the decimal system. Okay, from that perspective, I'll introduce binary. So let's suppose now if I write 1, so now you know that I'll just write 1 like this. If I have to write 2, I'll write 1 0. If I have to write 3, I'll write 1 1. If I have to write 4, I'll write 1 0 0. So 5 1 0 1. I am just increasing the bits. Okay. So if I write 6, 6 is 1 1 0. 7 1 1 1. Now I exhausted 3 bits. Okay. If I have to write 8, I'll write 1 1 1 1 1, probably 1 0 0 0. This is how I write 8. Okay, so now let me show you basically why do we write these things in this way. Okay, so all of these are placeholders, or bits I'll call. Okay, each bit is something physical. Okay, either it's a flip flop, or maybe howsoever it in computer's memory, it may be a magnetic tape. So there will be something. This is a physical thing. Okay, this bit is a physical thing, and now it's representation. This 1 comma 0 is an abstraction. How we represent is an abstraction, but these things are physical. They reside in the computer's memory. If it is in RAM, there are bits. Okay, if it is hard drive, we have bits there also. Okay, in registers we have bits. They have physical realization. So physical realization of these bits are flip flops, or maybe some magnetic tapes, or some other. So like we have SSDs nowadays. Okay, all these things, like what I write as bits, they are the abstraction of these physical realizations. This is an abstraction. Okay, now I am getting the physical world into a mathematical realm so that I can understand it. Okay, so what I am saying is, if you need to convert it into a decimal, because that is the number system we understand. We understand 1, 2, 3, 4, 5, 6 till 10. Actually, this system is called decimal. Why? Because there are 10 symbols in here. So we have 0 to 9 symbols. We have 0 to 9 symbols, and we sort of just use these symbols in order to count, or in order to represent anything. Okay, number systems are just representations. Okay, now how do we represent them? So we can label it like 0, 1, 2, 3. So I'm just labeling it numbers, number of the bits. So this is 0th bit, first bit, second bit, third bit. Okay, if something is written like this, if I write 1, 1, 0, 0. Okay, so how to convert this into decimal? Okay, the simple way is, because decimal works in, it has 10 symbols, so here we have only 2 symbols. So what we do is, we write 2 to the power this 3 plus, first whatever bit is, we will multiply that, 1 multiplied by 2 to the power 3, and then we have 1 over here, so we'll say, oh sorry, just need to zoom it again. For undergraduates, this is really important. Some people among you might know it, but it's really important so that you understand the bitwise operators. Okay, so here I said I'll write this 3, 2, 1, 0. So these are the numbers I did, this numbering I did on the number of bits. So after that I said 1 multiplied by 2 to the power this 3. Okay, then plus. Again there is this 1 bit, 1 multiplied by 2 to the power 2 plus, again 1 multiplied by this, because here we have 0 now, so 0 multiplied by 2 to the power 1 and plus 0 multiplied by 2 to the power 0. Okay, whatever here we have, we raised it 2 to the power, we raised it to the power, and then whatever these bits are, we'll basically just multiply them with these corresponding numbers. So this, if you see, this is 2 cube plus 2 square. So this number, if you see, is 8 plus 4. This is 12. Okay, in decimal system, this number is represented by 12. If you have to represent this in binary, so this is 1100 is 12. 1100 is 12. Okay, now let's suppose if you have to, again, there are different methods by which you can convert. I don't want to go in the conversion methods. There are a lot of materials available where you can learn to convert decimal from the integers from the decimals, or decimal from the binary and binary from the decimals. So right now, I just want you to understand that binary system is just one representation. Okay, if you have only two symbols, you have 1 and 0, and if you want to count, so now you only have two symbols to count with. You have to represent the information with only two symbols. That's what computers understand. It's not only with the any two-level system. Any two-level system where we have these two levels, we will use binary for that. Okay. Now you know that computer is a two-level system. It will use binary. So now let's suppose if I have to write 12. If I write 12 in computer's memory, how will it be stored? Okay. So I told you that there are three ways of representation of these integers. Okay. So the first representation is signed magnitude, then 1's complement, then 2's complement. In the earlier computers, we were using these two. Now in modern computers, most of the computers are using this. Okay, so this is what most of today's computers use. Now we need to see what signed magnitude is, what 1's complement is, what 2's complement is, and why do we use it this way. Okay, the signed integers basically means I am taking -1, -2 also into consideration. Okay, signed integers means like we have -100, we have +100 also. Okay, how to represent these? So let us first introduce the signed bit representation. So in the previous session, if somebody was there at the end, I was describing this. So in here, what do we do is we basically have one bit reserved. Okay, if we have this sort of, these are bits. Okay, these placeholders, I'll write them as bits. So this is called as most significant bit. This is called as least significant bit. Most significant bit, and this over here is called as least significant bit. Okay, so now if you see this MSB in this signed representation, if you see this MSB is used for sign. That's why it's called as sign bit. Okay, and then rest the bits are used to represent number. Let's suppose you have to represent positive numbers. So for positive number, this sign will be 0. So for positive numbers, sign bit is 0. Let's say you have to represent 5. So now you know that 5 in binary is represented by 1, 0, 1. This is 5. But you will use one additional bit to represent the sign. So here 0. This will be +5. Is it clear? Everybody with me? Okay. So in signed bit representation for positive numbers, we'll just write 0 as the most significant bit. Then it will be followed by its binary representation. This will be binary representation. Binary representation. Okay, and the first is most significant bit. If this is 0, then we have positive numbers. If this bit is 1, we have negative numbers. Okay, now you can clearly see that the problem is that for 0 we use two numbers to show it. Okay, so for zeros we'll use, let's say if somebody asks me write +0, so I'll probably write 0 0 0 followed by, if this is the most significant bit, I'll say this is +0. -0 is this is +0, and this is -0. If I'm using 4 bits, okay, there are for 0 there are two representations. Okay, so let's suppose if I have n bits. N bits means I have these n placeholders. So can you tell me what is the largest number, positive number, that I can store in n bits in this signed representation?
n-1 पे जहाँ पे आपने क्वेश्चन का आंसर दिया.
So the question that I asked was that if we have n bits, so what's the maximum number that you can represent by using this signed magnitude representation? So in that we said that the first bit will be stored. This will be used for the sign. This is sign bit. Now we have just 3 bits left. Okay, so that's why we said 2 to the power n-1 minus 1. Why? If we gave the 1 1 1 to this number, so that's each of these bits, they can hold two values. Okay, 2 2 and 2. So if you know permutations and combination, you can come on to this 2 to the power n-1. Okay, why -1? Because the most number that you can store, let's suppose 3 bits, is 7. It's not 8. it is minus 1. 2 to the power 3 minus 1. Okay, so that's why 2 to the power n minus 1, because we have n bits. One bit was used for the most significant bit was used for the sign, then rest 3 bits. That's why we got the this 2 to the power n minus 1, and then minus 1. Basically we have to subtract 1 from this 2 to the power n minus 1, so as to get the largest number. Similarly, I said that negative number also will be this, because first number will be, this will be, if you have negative, this will be minus, this will be 1, this is negative number. If this is 0, this will be positive number, and rest, if these bits are positive, now it will be plus or minus 7. So here now coming to this one's complement. So in that I said that if the positive numbers are there, so they'll be represented same as they are represented in binary. Okay, let's suppose we have this 5. So if you consider that a number is stored in 8 bits, okay, 5 let's suppose is there, and if you want to store this in a computer's memory, if the computer is using one's complement, so what will you do? So we'll just use its pure binary form. This is the directly binary. But if it is a negative number, so what you will do is you will basically use one's complement of this 5, one's complement of 5. So what is this one's complement? Basically you will just flip the bits, you invert all the bits. So if this is 5, if you invert the bits, it will become minus 5. 1 1 1 1 1 0 1 0. So this is minus 5. Okay, this is one's complement. Okay, that's what we call a one's complement. If you have a bit binary representation, you flip invert all the bits, then you get you basically get a one's complement of that. Okay, the modern computers, what they do is they'll use 2's complement. I'm just rushing through it because we'll go to 2's complement. There's a lot to discuss about one's complement number system, but I just want you to give the gist why are we studying about these different number systems. So 2's complement, in that what we'll do is, the first thing is positive numbers and negative numbers. How do we represent them? So in 2's complement, if you see, first we'll see what 2's complement is, then we'll go to this representation. So let's suppose you have a number 5. Okay, the number 5 in binary is represented by 101. Okay, in 8 bits it is represented like this. Just hold your questions, I'll just come back in a couple of minutes. So this is 5. So if you take 1's complement, you know that we have to invert all the bits. So inverting all the bits means 1 1 1 1 1 0 1 0. Okay, now if you have to take 2's complement, you will add 1 over here. Okay, in the 1's complement, if you add 1, you will get the 2's complement. So for that, what you will get is, you will basically get 1. Okay, and then you will get again this 1. This is again rest of the zeros. Okay, and then you will invert. You will be basically, you are adding it, so you will get this. So this is the 2's complement representation of 5. Okay, I'll just pause here because somebody has a question. So everybody is with me. I said this is 5 and this is its 1's complement. If you invert the bits, so 1's complement is invert the bits. And then I said if you have to get 2's complement, you take 1's complement and add this bit 1, basically add the least significant bit. You just add this 1 and you get the 2's complement. I'll tell you a shortcut to basically just go from this binary to 2's complement. So let's suppose we had this 101 0 0 0 0 0. This is 8-bit representation of 5 in binary. So if you directly want to go to 2's complement, okay, what you have to do is, okay, see where you got the first bit. Let's suppose you got the first bit over here. If you see, this is the first most significant one. You just need to see that bit. So just copy that as it is. Okay, invert all the bits. Okay, this is then 1, this is then 0. Okay, this is then 1 1 1 1 1, something like this. Okay, you directly go to this 2's complement representation. And in 2's complement, I'll tell you that these ones mean nothing basically. Okay, if you have to go from 2's complement to decimal, 2's complement to decimal, there is again a conversion. So how do we do that? So let's suppose 1 0 1 1 is 2's complement. Say it's 2's complement. So if you have to go to, let's say, binary, so what do we do is, this is 0 1 2 third bit, 0th bit, first bit, second bit, and third bit. So you write minus sign first. For this bit you will write minus 2 to the power 3. Okay, then you will add. So 0, it won't get added. 2 to the power 1 plus 2 to the power 0. So if you see, this is minus 8, this is plus, this is 2, this is plus 1. So this is minus 5. So this is the representation of 5. So I said you, if you have to represent now, let's suppose positive numbers and negative numbers. So what you will do? So this is, suppose 5. So 5 will be represented something like 1 0 1 0 0 0 0. Okay. Now how to get its 2's complement? In order to get 2's complement, I told you that you have to say, keep this 1 as it is, make this 1, make this 0, and make this 1. Okay, rest it will become basically 1's. So in 2's complement, these won't matter now. Why won't they matter? Because I am writing 2 to the power minus 2 to the power this. This will cancel all the ones till here. Okay, so this representation 1011 and 1111 1011 they are equivalent in 2's representation. Why? Let's do that. Let's do the computation. So this is third bit, second bit, first bit, zeroth bit. So minus 2 to the power 3 plus 2 to the power 1 plus 2 to the power 0. Okay, so this over here is equal to minus 5. So if you see this, so this is 7th 6 5 7 6 5 4 3 2 1 0. So minus 2 to the power 7 plus 2 to the power 6 plus 2 to the power 5 plus 2 to the power 4 plus 2 to the power 3, okay, plus 2 to the power 1 and 2 to the power 0. So if you see over here this, so this is minus 128, okay, till here. So let's suppose this is 64, this is 32, this is 16. So this over here is again, if you see, this should be 128. Okay, plus this. I think plus then this we have 2 to the power 8. This is 8. This is plus 2 and this is plus 1. So if you again compute this, if you again compute this number, this should come to minus 5 basically. Okay, can somebody confirm this? So if you have this 128, because all the bits, if you set all these bits till here, if you set all these bits, it'll be 127. So if you set this bit and rest bits are 0, it'll be 128. I'm performing maybe mathematical calculation a bit faster. I'll slow down a bit. So here, if you see, this is minus 2 to the power 10. This is minus 128. Okay, the maximum value for all these bits can be 127. Okay, if all the bits are set from here to here, that's 127. So if you have 1 0 0 0, so this is 8. The maximum value of these 3 bits, if you get, can be 7 1 1 1 1. Okay, this can be 7. So that's what I'm saying over here. So this is minus 128. The maximum value of all these values added together can be at most 127. Okay, so that's why if you see this representation and if you see this representation, this basically is equivalent, because we don't care about these ones. They are called as leading ones. So these are leading ones. We just care about this one. If there is one, and then there's a run of ones. So this is basically equivalent in 2's complement. I hope this is clear. Maybe if this is not clear, watch this again and this will be clear. So nowadays computers use this type of system to represent in computers memory. So 5, let's suppose if you have 5, if you have minus 5, so accordingly we'll use 2's complement representation, okay, to represent this. So let's suppose for this 5, we'll just use 0 0 0 0 1 0 1. If you have a negative number, so how will you use? You will just use this 2's complement representation, 2's complement. Okay. Now let's come to the bitwise operators. Everybody clear with this? I don't assume that you got everything that I spoke so far, but I came to this 2's complement representation. This is how computers nowadays represent numbers in the memory. Okay, they represent numbers in the 2's complement. Now we'll come to the bitwise operators, because everything will now happen at bit level. So what are operations we will do that will happen at bit level? There is a lot to talk about these number systems. Okay, I would have talked about this access. This 2's complement is basically called as access k representation if there are k bits. So I won't go into that. I think you guys will cover that on your own. But here I needed your attention basically over here. So where we need to represent numbers in computers, and in computers memory, we represent these numbers in 2's complement. So if there's a positive number, we represent that in binary. If there's a negative number, what we do is we take its 2's complement. Okay, we take its 2's complement and then represent that in the computer's memory. Now we'll come to the bitwise operators. Now you know how these numbers are represented. It should be easy to grasp these operators. So how many bitwise operators we have? We have AND, okay, we have OR, we have NOT, we have XOR, and we have left shift, and then we have right shift. These are the bitwise operators. This is AND, this is OR, this is NOT, this is XOR, this is left shift, this is right shift. These are all the bitwise operators that Python supports. Okay, so we'll take each of them one by one. I think this is somewhat similar to whatever we had in logical and logical or logical NOR. The truth table is similar. So here, if you see this AND operator, so it takes operands as bits. The operands are bits. Okay, so what's the truth table? So if this is, let's suppose bit A, if this is bit B, and if this is A and B. So let's suppose this is 1 1, so this will be 1. If this is 1 0, this will be 0 0 1. This will be 0 1 1. It will 0 0 will be again 0. This is how we'll perform AND operation. Okay. Now let's take an example of this. So if I have a number A is equal 10, okay, and I have B is equal say 20. What should be A and B? Question to you guys. So what I asked is, I said if we have a number A that's equal to 10, and then we have a number B that's equal to 20, and we'll perform bitwise AND A and B, what should be the answer? Mahmood said true. That's the first misconception. So here, if we have this AND operator, I told you that it operates on bit level. So what will happen is, this will convert this A into bits. Okay, what is the bit? What's the binary of this 10? So it will be 1010. Let's suppose we are working with 8 bits. Suppose. Okay, what is the binary of 20? Okay, binary of 20 is, we have 16 and we have 4. 16 4 is 20. I hope this is the binary. Okay, so this is the binary. Can you just confirm it if this is the binary of 10, and now after that you are performing the AND operation. Okay, I'll just check the binary of 20, because in Python we have a function by which we can check, that's bin. So I'll just write Python 3. So bin of 20. So that is 10. Oh, so this should be basically 0 0 1 0 and then 0 0. This is a representation. Okay, everybody with me? So this is my A and this is my B20.
One is missing.
The one is missing. Where is that? It's here, huh?
Hmm.
So this is the binary representation. Okay, that shows me I cannot copy even from the screen. So now if you perform the AND operation of all of these bits, bitwise AND. So first you will perform AND of this bit. 0 and 0 is 0. 1 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 0 and 1 is 0. So everything will be 0 0. Okay, so now if I run it, the answer should be 0. So let's do that. Okay, let's suppose A is equal 10. Okay, B is equal 20. A and B. This is bitwise AND. Voila, this is 20. This is 0. Okay, is it clear? Now if you understood this, I'll give you one more problem. Okay, let's suppose A is equal to, again the same 10, B is equal to 21. So what should be the answer? So here the bitwise operators, they don't answer true or false. That is what logical operators do. Logical operators, they get true and false. Okay, they get this as an input, true and false, and they'll give you some true and false. Actually, if you see this, so if you see at bit level, they'll give 1 and 0. 1 and 0 basically means true and false. But as a whole, when you read that number, let's suppose it gave something like this, 101 and 010, something like this. So if you perform bitwise AND, so for each bit, it is giving true or false for each bit. 1 and 0, this is 0. 1 and 0, this is 0. And this is also 0. Now when you read it, okay, when you read, the computer reads this number, reads this representation 0 0 0. So for us that is 0, because Python will give us the decimal representation. So in that it is decimal. So at each bit this will be true or false. But once you have a pattern of bits, that you read as a number. Okay, in decimal, particularly Python will read this as a decimal number. So it will throw this decimal number towards you. So now the question is that if you have this A is equal to 10 and B is equal to 21. B is equal to 21. So at bit level, so everything will be true and false. But once the representation is over, so computer will read it as a decimal number. So now let's do that. A is equal to 10. That means 1010 and 00. These are 8 bits. I'm just doing the computation in 8 bits. 21. So 21 will be this same, but here it will be 1. So it will be 0001 10. This is 16. This is 01. This is
Triple one.
This is 0101 0101 0101. Okay, this is the representation, not triple one. So if you see over here, this is 0 1 2 3 4. Okay, this is 2 to the power 4 is 16, 17, and this is 2 to the power 1. This is 17, 18, and this is 19. Let's see if if the representation is right. Okay, whatever it is, I think representation you guys can just check with the Python if there is some confusion. So by bin of this 21, this should be 10101. Yes, this is the right representation. Okay, so now if you compute this AND operation, now this is AND operation. So 0 and 0, this will be 0. This will be 0 0 0 0 0 0 and 0. Okay, this again should be 0. Okay, at least whatever we saw, it should be 0. So let's suppose we'll run it on our Python interactive shell. So if a is equal to 20, b is equal to a is equal to 21 rather. So let's just clear this. A is equal to 21, b is equal to 10. What is a and b? So that's 0 again. Now I'll write some number. I'll write a is equal to say 32. I'll write some random numbers. B is equal to 45. A and b. So a and b, if you see here, came 32. So now we'll have to justify this answer. Okay, if you see this, so we came a is equal to 32. I'll write it here. So a is equal to 32, b is equal to 45. Okay, now we'll have to justify how this a and b is equal to 32. Let's first check what is the binary of this a. So this should be 1, it should be 0, 0, 0, 0. So this is 2 to the power 5. So this is binary of 32. So if you want to check it, so just go to the Python binary of 32. So this is 1 followed by 4 zeros, 1 followed by 1, 2, 3, 4, 5 zeros rather. Okay, so this should be over here. Okay, this is 2 to the power 5. And then a binary of 45. So this is 101, 1011, 101 over 1 here, and then we have 01, then this is 00. So this is 45. Okay, so this is the binary representation of 32. Okay, this is the binary representation of 32. I'll just unhide this. So this is 32 and this is 45. Now we'll see a and b, it came out to be 32. So why is this so? So now let's perform the bitwise AND operation. 0 and 0 is 0, this is 0, 1 and 1 is 1, this is 0, this is 0, 0, 0, 0. Have we written, wrote that, did we write that accurately? I don't think so. Let's see if we wrote it exactly what it was. So this was 1 0 followed by 1 1 0 1. That's 45. 1 0 1 1 0 1. 1 0 1 1 0 1. Okay. Now what do we perform? We performed A and B. Okay. Yes. So here, if you see, this is 32. This over here is 32. I just wanted to cross check. Is everybody with me? Are you following? I just wanted to cross check, so this was right. So here, this is the representation of 32, this is the representation of 45. When you performed AND operation, you got this. Now let's do the same thing. Let's perform a OR operation with this. Okay, this is my A and B. So what I'll do is I'll perform A or B. Okay, A or B is 45. Can you tell me why? Can you just do the bitwise OR operation on these and you tell me why is it 45? If my A is 32 and B is 45, A or B, this should be equal to 45. Can you check it? So now we saw how OR operates and we saw how AND operates. Okay, NOT is basically just inversion of bits. If you have NOT, it will just invert bits. Let's suppose we have this 32. 32's representation is 0, 0, 0, 1, 0. Okay, 0, 0, 0, 0. This is the representation of 32. Okay, this is 32 in binary. So what I'm saying is, if I invert this, if A is equal to 32, if I write NOT of A, okay, if I print it, can anyone tell me what will happen? And what will be printed basically? There's a question to you. What I'm saying is, I'll say A is equal to 32. Okay, then I'm saying I'll invert this A. So A naught of A. Okay, I wanted to print this on the screen. So what will be printed on the screen?
I think in that case it should be 13
Okay,
minus
so what will
36.
happen first? So whole of
It
these
will,
bits will be flipped.
yes,
So it
the
will be
whole,
1 1 0 1 1 1 0 1 1 1 1 1. Okay, this is what will happen in binary. But there is a catch over here. So if you see the catch, you know now that this is a negative number. Okay, this is a
Hmm.
negative number, so it is in 2's complement. You have to, this is your number 1101. So 1101. So then we have 1111, 1111. Okay, so this is a number that's in 2's complement. I told you that everything in computer's memory will be seen as 2's complement if you see it like this. So now you need to convert this. So this is 0 1 2 3 4 5 6 7. So this will be minus 2 to the power 6. So I'll just write the flip of this bit. So plus 2 to the power 4 plus, I think this is 15. The whole of this is 15. So this is rather this is 16 plus 15 plus minus, this is plus, and this is minus 64. So what are the number is there? This is 31. Okay, this over here is 31 plus 64 minus 64. So what is this? So this is 3. This should be 33 minus 33. This is what is expected. Okay, if this is happening. Okay, let's see if we get the same result that we compute. Otherwise, computation will be wrong. So let's go back to the VS Code and we'll see if we get the same result. So over here, I said that if you have a is equal 32, so we said a is equal 32 will perform not of a. So I'll say not of a. This is minus 33. Did you see it over here? Is it visible on the screen? Over here, if you see, I said a is equal 32, then I said not of a, then I said this is equal 33. That we computed on the paper first. Okay, this was my representation of number because I flipped the bits. 45 was, this was my 45. If you see it over here, this was my 32. This is the representation of 32. So when I flipped the bits, this is what it got flipped. But I know that computer represents the number in 2's complement. I know this is some 2's complement number. Computer will read it as 2's complement. So if you see in 2's complement, this number is minus 33. That's why it was printed on the screen minus 33. Now again a question to you. Okay, the question will be very simple. A is equal, suppose 12. So if I say not a, what is this equal to? So actually, let's suppose we have a that's equal to 32. Suppose this is the number. Okay, if I perform not of a, okay, what will happen? So not is a bitwise operator. So 32, how is it represented? 1 followed by 5 zeros. Okay, so this is 4 zeros and this is another 0, 1, 0, 0. I'm writing in the 8 bits. Okay, this is 8-bit representation. 8-bit. So no matter how many bits there are, it will be again zeros over here. So I'm saying that you have to apply not of a. Okay, so not of a, if you see, is, so you will just flip all the bits. So this will become 1, this will become 1, this will become 0, this will become 1, 1, 1, 1, and 1. Okay, now I know that this number is stored in the computer's memory. Okay, computer will represent use this as, it will be read as 2's complement number. Okay, irrespective howsoever ones there are. Let's suppose I just restricted myself to 8 bits. If the number is stored in 8 bits, it can be stored in 64 bits. There will be a run of ones over here. So but I said in 2's complement, this run of ones doesn't matter. So now what I'll write is, this is 0th bit, first, second, third, fourth, fifth, sixth, and 7th bit. Okay, the first bit's value I'll write minus 2 to the power 7 plus 2 to the power 6 plus, actually this is 2 to the power 5 but multiplied by 0, nothing. So 2 to the power 4 plus 2 to the power 3, 2 to the power 2, 2 to the power 1 plus 2 to the power 0. Okay, that's what I did over here. Okay, now what I'll do is, so this 2 to the power 7, this is equal to minus 128 plus this is 64 plus 16 plus 8 plus 4 plus 2 plus 1. Okay, now if you calculate this, this should be equal to minus 33. That's what I got over here. But here what I did is, I just removed this bit. 2 to the power 7 bit I removed. Okay, because for this I just start from here. So if you say minus 2 to the power 7 plus 2 to the power 6. Okay, what is this equal to? So this is minus 2 to the power, this is minus 128 plus 64. This is again 64. Okay, so better I could have just wrote like this. I could have just removed this is minus 64. I could have just added minus over here. That's why these ones don't matter. I hope this is clear now. If I have, let's suppose 1 1 1. Okay, if I write this is, let's suppose 8th bit, 9th bit, 10th bit. What I'm saying is, you can remove these two bits and you can just start from here, because this is, let's suppose 8, 9, and 10. Okay, this is 10th bit, this is 9th bit, this is 8th bit. So actually the formulation is minus 2 to the power 10 plus 2 to the power 9 plus 2 to the power 8. So what I'm saying is, I'm saying this is equivalent to minus 2 to the power 8. That's what I'm saying. Why? Because 2 to the power 10 is minus 1024 plus this is 5 and 2. This is 256. Okay, 256 plus 5 and 2. Okay, this basically will give you this minus 2 to the power 8. So this should be equal to 256 minus 256. That's why in 2's complement, these leading ones don't matter. Okay, wherever you see the first one. So if you see something like this, 1 1 1, a run of ones, then you see 0 1 0 0 0 1. Okay, and you have to convert this into let's suppose decimal, and this is in 2's complement binary. So you won't care about these ones. You won't care about these ones, and you will start it from probably here. Because why? The effect of this is because this number is negative, and then these numbers are positive, and they are cancelling the effect of each other, just leaving this one behind. Is it clear? Mahmoud, is it clear?
Yes, it's clear, very clear. Thank you.
So that's what I'm saying. A, if you have, is equal to A. Now let's suppose we take another example. A is equal to 10. So 10 is A is equal to 10 basically means 1 0 1 0 and these four zeros. So if I say not A, so not A will be 1 1 1 1 0 1 0 1. Now you know that this number will be read as 2's complement. So how will computer read it? So it will be read at this is 0th bit first, second, third, fourth, fifth, sixth, seventh. Now you know that these bits we don't care. We'll write from minus 2 to the power 4 plus 2 to the power 2 plus 2 to the power 0. Okay, this is minus 16 plus 4 plus 1. So this is minus 11. So if I write A is equal to 10, if I flip it, okay, I'll go to the VS Code, I'll show you there. So if you see over here, I'll write A is equal to 10. If I say not of A, that's minus 11. If you see it over here, that's minus 11. So I'll just turn to the VS Code, okay. So this is over here. So I'll clear the screen. A is equal to 10, not of A is equal to minus 11. Is it clear on the screen? So over here, A is equal to 10, not A is equal to minus 11. Any questions? Okay, now we have seen what AND does, what OR does, we've also seen what NOT does. Okay, they operate, one thing that you have to remember is they operate at bit level. Okay, if you take individual bit, the answer will be 1 and 0. But once you have the run of these bits, so that will be read as decimal. Okay, a run of bits is read as decimal by our computer. So our computer, what it does is, so each of the bit will basically just give us one answer. It will give us either 0 or it will give us 1. Okay, that's why I said if A is equal, let's suppose 5, B is equal, say 6. Okay, if I perform A and B, so what will happen is, so A will represent 1 0 1. Okay, let's suppose we are representing 4 bits. So B is 6. So this is 4 to 6. So this is the representation of A. This is the representation of B. If I perform AND operation, AND will happen first with this 0 and 1. This is 0. This is 0 and this over here is 1, this over here is 0, this over here is 0. So 0 1 0 0 is the output. Okay, so what is this? This number is basically equal to 4. So if I perform A is equal to 5, B is equal to 6 and I perform AND of these, okay, let me show it on the screen so that it's clear to everyone. So let's suppose A is equal to 5, B is equal to 6, A and B. Now you saw that this is 4. That's what I wrote over here. This is 4. Okay, now we saw AND, again similarly OR is there and then we have NOT there. So be careful in the NOT because it flips the bits. If you write a positive number, it will flip the bits. Okay, be careful in this NOT operation. So in that it will flip the bit and then we'll have to read the number in 2's complement form. Okay, so these are 3 operations that we saw so far. And then we have XOR, then we have right shift and left shift operations. Okay, now let's go on and the confused operator, that's XOR. So this OR operator, this is called as inclusive OR. Okay, this is called inclusive OR. Why is it called inclusive? So if you saw the truth table of the OR, so we have A, B and we had this OR operator. Okay, in that this 1 and 1, it was also 1, this 1 and 0. So inclusive 1. Okay, so this was again 1, 0 and 1, this was again 1, so 0 0, this was 0. So only this entry was 0. If there is no 1, if there is no input that's turned on, then the output becomes 0. So but what is exclusive OR? So exclusive OR means, so wherever the input is high or low, so let's suppose we have this 1 1, so it will be off. This is A XOR B. This is how we write it, A XOR B. This is A or B, A or B. XOR is 0 in these two things. Exclusive OR means only this should be there. There should be exclusively OR. One of them should be OR. That's 1 or 0, 0 or 1. If there is both the inputs are high, then it's 0. If both the inputs are low, this is again 0. This is called as exclusive OR. So it can be also performed within 3 bits. Let's suppose we have A XOR B XOR C. Okay, now we have these bits A XOR 0 XOR, let's suppose 1. So how will you do it? Let's suppose you can do it like this. 1 exclusive OR is 1. Exclusive OR 1 is basically 0. Okay, otherwise there is one more method to do it. Okay, if you have a lot of symbols over here, so now then it becomes difficult. You have to club two things together. So this exclusive OR operation is also called as modulo 2 operation. Modulo 2. What is that modulo 2? Let me tell you that. So now let's suppose we have this 1 XOR 1 XOR 0. XOR 0, XOR 1, XOR 1, something like this. Okay. So what you will do is you basically will just count the number of ones. So 1, 1, 1, 1. How many number of ones are there? 4. Okay. Then you will take modulus with 2. So what is the modulus? You will take the remainder. So this basically is 0. So whole of this will be 0. Okay, if you again apply the same rule over here, 1 plus 1 is 2, 2 modulo 2 is 0. 0 plus 0 is 0, 0 modulo 2 is 0. And these things are 1. 1 plus 0 is 1, 1 modulo 2 is 1. 0 plus 1 is 1, 1 modulo 2 is 1. That's why it's called as mod 2 gate, we can write it, mod 2 operation. Is it clear how XOR works? Please focus here, this is really important. Okay, how XOR is done is, we call it modulo 2 operation. So in that, if you have A, B, C, D, E, F, these are the bits, okay, and these are XOR bits. So what I'm telling you is that just do one thing: count the number of ones, count the number of ones that are in there, and then take modulo operation with 2. Whatever is the remainder is your answer. Okay, if you have 1, 1, 0, 1, 0, 1, something like this, and we have to perform XOR of these things. So what we'll do is 1, 2, 3, 4. 4 modulo 2, that's equal to 0. So this whole will be equal to 0. Okay, if we have 1, 1, 1, 0, 1, 1, and 0, suppose. So 1, 2, 3, 4, 5. So 5 modulo 2 is 1. Okay, basically taking the remainder. So that is equal to 1. So this whole expression XOR operation is 1. So is XOR clear? Can I assume that XOR is clear for you guys? Now I hope that this XOR operation is clear. So this XOR operation is also clear. So XOR, just remember that this is called as modulo 2 operator. Modulo 2 operator. So in this, what we do is, howsoever number ones you have, and then you will take just basically the modulo 2 of that. You just count the number of ones and just take the modulo 2. Let's now take the question. A is equal 10, say B is equal 15. So if I write A XOR B, what should be the output? Now this question you should get answer. Otherwise, I'll think that you haven't understood bitwise operator, neither you have understood XOR. The question is that A is equal 7, B is equal 9. So what is A exclusive or B? So if you see it over here, A is equal 7, that means 0, 1, 1, 1. This is 7. B is equal 9, that is 8 plus 1 is 9, 1, 0, 0, 1. Now if you perform exclusive OR, so 0 exclusive OR, 1 is 1, this is 1, this is 1, 1 and 1 is 0. So what is this number? So this is 8, 4 and 1. So 8 plus 4 plus 1 is equal to 13. Okay, if you don't trust my calculation, we can do that. This should not be 13. I think this is 8, 4 and 2. So this is 8 plus 4 plus 2. This should be 14. So let's do the calculation. Let's use the Python to ascertain our calculation. So here if you see, A is equal to, what was A is equal to? A was equal to 7 and B was 9. A was 7, B was 9, A exclusive or B. That's 14. Now I hope that you got some hang of these XOR operations. So now so far what we have done is, so we have covered 4 operations now. So if you see bitwise 4 operations we have covered. We have covered OR, AND, NOT and exclusive OR. Okay, now last 2 operations we'll cover. That's called as left shift and right shift. These are the operations that we'll cover. So what you do is, let's suppose this is the run of bits. So it is stored in some register, let's suppose. It's stored in register. So I'm speaking about right shift and left shift operations. Okay, so if we have this, let's suppose we have number written over here. So these are, let's suppose, bits 1 0 1 1 1. Okay, so if I'm doing left shift means I'm shifting it left. So what will happen is, if I'm doing left shift once, so what will happen is, so here it will be 0. So these bits will be shifted by 1. They'll be left shifted by 1. So it will be 1. So 0, this is 1 1 1 now, because everything will get shifted. So this is 0 and then these 3 bits will get shifted. So actually we had 1 2 3 4 5 bits. So what will happen now? This is 0 1 1 1 0 and 1. And if it's only these many bits, so one bit will basically get dropped off. So if you see, we got 0, then we got triple 1, then we got 0. Okay, so this is called as a left shift. Left shift. If you have right shift, so right shift basically means you are shifting towards the right, you are dropping one bit at the end. So you had this 1 0 1 1 and 1. So right shift basically means you right shift it, you shift it towards right. So that means you will drop this one. So what you will write is, so you will drop this one, so this bit will get shifted like this. So 1 will get shifted over here, then 0, then 1, then last one, because now we shifted here, we'll get 0. Okay, we got 1 bit drop because we had 1 2 3 4 5, 1 bit got dropped, we are left with only 1 bit. Okay, now let me show you the magic of this operator. Let's suppose you are writing the number 101. This is the number, this is number 5. Okay, this is number 5. So what I do is, if I left shift it once, so what will happen is I'll get a number 1010. Everybody agrees with me? I'll shift these bits by 1, left shift by 1. So what will this number be equal to? So this number is equal to 10. So this operation basically is equivalent to multiplying the number with 2. Okay, if you shift it once, you are multiplying with 2. If you shift it again, you are again multiplying by 2. Okay, number of shifts basically means number of times you are multiplying that number. Okay, if I now have a number, let's suppose 4. So this is my number 4. Okay, so if I have to left shift it, I left shift it, so left shift will make it. So if I just shift it like this, so this bit will get shifted, so this will be 1 0 0 0. Okay, so what is this number? This is 8. This was 4. This is 8. If I again left shift it, this will 1 0 0 0 0. Okay, I'm shifting the bit, so this will be 16. So left shift operation basically means this is equivalent to multiplying by 2. Okay, if you have to now multiply any number by 2, it's better to left shift. Okay, let's do it in the code and we'll show it there. Okay, and now I'll show you the VS code. So come on here. So here, if I have, let's suppose a is equal to say number 4. Okay, so 4 left shift by 1, let's say, or a left shift by 1, a left shift by 1, this is equal to 8. Okay, if I have number, let's suppose 50, I left shift it by 1, so what will happen is it will get multiplied by 2, so this will be equal to 100. If I 50 left shift by 2, so it will get multiplied by 2 twice, that is 2 to the power 2, it will get multiplied 2 to the power 4, so that is 4 multiplied by 50 is 200. So if you see it over here, so now if I right shift it, right shift basically means dividing by 2, so 50 right shift it by 2, that means you are dividing it by 2. Okay, you are dividing it by 2 by twice, so that's why here the division basically is floor, that's why 50 right shift twice, we got 12, otherwise it should have been 12.5, but 0.5 is truncated. 50 divided by 2 is 25, 25 divided by 2 is 12 point, let's suppose 50, we'll shift it by 1, so this is 25, 25 we'll shift it again by 2, oh sorry, 25 will shift it by 1 again. Okay, that's 12. Okay, because it's 12.5, I think, or yeah, 12.5. Let's suppose now we have a number 30. If we right shift it thrice, so what will happen is it will get multiplied by 30 multiplied by 2 to the power 3. So this is 30 multiplied by 8. So this is 240. So if you see it, oh, this is actually left shift, so I should have left shifted over here. So this is 240 if I left shift it. So now if I, let's suppose I have a number 40, if I left shift it by say 4, so what will happen is this is 40 multiplied by 2 to the power 4. 2 to the power 4 is 16 multiplied by 40. Okay, and this is 0, 624, this is 640. You can see that. Is it clear? So what is left shift operator? So left shift operator will basically multiply it 2 to the power that number of times. Okay, and right shift operator will divide it 2 to the power that number of times. Is it clear so far? So now if you are a good programmer, so what will you do if you are a good programmer? So if you sometimes see you are multiplying a number which is power of 2, let's suppose you are multiplying something with 64, you should not do this. You should rather, let's suppose you have a number a where you are multiplying by 64. So this a into 64 is equal to 2 to the power a into 2 to the power 6. Now you know that I don't need to perform this because it will use arithmetic logic unit. So rather a better way is a left shift it 6 times. So basically this will happen at CPU level. It will just move the register. Okay, and just bit shifting will happen. Is it clear for everyone? So this operation is faster. Let's suppose you have a multiplied by 256. Okay, what will you do? A multiplied by 2 to the power 8. So this is basically equal to a left shift it 8 times. Is it clear? Nice. So this is the first trick that I wanted to show you. Okay, the first thing that we saw is that if you want to multiply a number which is power of 2, you can left shift. If you want to divide a number which is again a power of 2, you can again use right shift. Okay, now once you see this multiplication, if you see a power of 2, that's why you should remember the power of 2's. So this 2 to the power 1 is 2, 2 to the power 2, this is 4, 8, 16, this is 32, this is 64, this is 128, this is 256, this is 512, this is 2 to the power 10, this is 1024. Okay, that's the reason we say that 1 GB is equal to 1024 MBs. Okay, because there we have these many number of bits. Okay, these many number of, if we have, let's suppose we have 1024 bits, we call it 1 megabyte. We call this 1 megabyte, but usually, sorry, we call it 1 kilobyte rather. So this kilo basically means 10 to the power 3. But here we don't measure in powers of 10. We measure in powers of 2. So this kilo in computer science means 2 to the power 10. Okay, mega means 2 to the power 20, giga means 2 to the power 30. Usually kilo means, in scientific notation, kilo means 10 to the power 3. Okay, mega means 10 to the power 6. Okay, giga means 10 to the power 12, I think. You should check it. But here, if you see this, kilo means 2 to the power 10, mega means 2 to the power 20, and giga means 2 to the power 30. Because we measure in the powers of 2, we don't measure in powers of 10. Is it clear? How many of you are happy that you at least learned this? 2 to the power 10, we measure in 2 to the power 10. That's why our 1 gigabytes is equal to 1024 megabytes. It's not just 1000 megabytes. Okay? I hope that this is clear. Now the first thing that we saw is where you can use these operations. I'll show you one more magic trick. Okay, one more magic trick. Let's suppose if I give you a thing, if I want to show you that if a number is even, how will you do that? If a number is even or maybe odd. Usually how programmers write, like if we have a, so what they do is they'll say a modulus 2 is equal to 0. Okay, if this is the condition, that it's even, else odd. So how many of you write the programs like this? Okay, you see that if a modulus percent 2 is equal to 0, and then this is even or this is otherwise odd, and this is very cheap operation. By cheap, I don't mean this is cheap in terms of hardware. This is cheap in terms of programming. Okay, why is it cheap? Because it takes a lot of hardware cost. It uses arithmetic logic. First, it will perform this operation. Then it will use comparison. Okay, now I'll show you a better way how to perform this operation. So if you have a number a, okay, if you want to check if it is even or odd, see at the bit level. See at the bit level. If you have number 5, okay, 5 is odd number. Last bit, if you see, this is always 1 for the odd numbers. For the odd numbers, last bit is set. Set means it's 1. Okay, for 5, last bit is 1. Now what you will do is, you can say 101 and ampersand it is 1. So if you ampersand it with 1, what will happen is, so everything is 0. So these will become 0 and last bit will be 1. So if a and, okay, if a and 1, so this will give result as true. A and 1 is true. Okay, so it is odd number. A and 1 basically will result in 1. So that 1 in C or C++ is treated as true. So you need if a and 1, you will directly say it's odd, else even. Okay, in Python what you will do is you will say if a and 1 is probably equal to 1. So here it will just perform bitwise AND, which is faster, and then it will compare it with 1. Okay, let's show you, let me show you that. But in C, this is the or C++, this is the code you need to write. You don't need to even compare this thing. Let's now go back to the coding window and I'll show you that. We have a number, say we have a number a is equal to 21. Now I know that last bit is set. So what I can write is a and 1. So you will see that it'll give me the 1 as answer. This is 1. Okay, so if I write a, if a and 1 is equal to 1, so what is this? This is odd number. So that will tell me this is odd. Print odd, or maybe I'll write like this, print odd. Whatever it is, it will throwing me the error. So because I need to do the indentation right. So suppose a is equal to 20, I'll write it here. A is equal to 21. So if a ampersand 1 is equal to 1, print odd, else print even. If I save this code, I have to go back. This is ls. We have a test dot there. So there's Python 3 test.py. So here you saw that this is 20 is odd. So if you now write it like this, 26, I saved it, the program. If I go back, this is even number. So from now onwards, how will you write the code? You won't write the code that a modulus 2 is equal to 0. What you will do? We'll just use this ampersand operator. Maybe you can also use the OR. The crux is that for odd numbers, last bit is 1. So if you can use OR, so what you can do with the OR is, so let's suppose we wrote OR. This is 1. Anyways, OR can't be used because it will anyways give 1 back for the both the numbers. Okay, so even odd, how many for how many guys this even odd is clear by using this and operator, by using the bitwise and operator. Now that you understand the basics of bitwise operations, we are done with this because you know how numbers are represented, and then if we do this and that operation, what will happen? Now we'll see their usage. Okay, that's where this magic miracle happens. Okay, this is, I'll say, plus 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 beauty. This is really beautiful. If you see these things, this is really beautiful. The first thing that we'll say is how to basically use them as flags. Because I talked about flags, that I said that if you, let's suppose you keep a variable for flags usually. Okay, you keep a variable for flags. Okay, flag will be, let's suppose, an integer, which will be either 1 or 0, let's say. So with bitwise operators, if you have a single number, you can use it for multiple flags. Okay, let's suppose you used a, and now this number is suppose having 8 bits. So it can be used for 8 flags. Okay, now you only need a mechanism. What mechanism do you need? You need a mechanism to read each bit. Okay, and you need to write on each bit. So by flag, I'll just tell for the people who haven't programmed much. So sometimes we use flag. If something happens, we'll say this turn on this flag or turn off this flag. Okay. I just gave the example to Mahmood that in microprocessor we have multiple flags. In processors we have different flags. So in programming also we use some flags. So let's suppose if you want to say that if a number is even, I'll set this flag as 1. So if this flag is set to 1, then I'll do something else. Okay, in control flow that we'll learn. But here if you see that, usually what people do is they'll use a whole integer for the flag. They'll say, I'll say a flag 1, and they'll put it equal to 1. And then probably what they'll do is they'll set and unset this flag. But what I'm saying is with these bitwise operators, the beauty is that if you have an 8 bit, because you know the integer usually occupies, let's suppose 16 bits or 8 bits, you can use it for 16 flags. The only capability that you want is you should be able to read each bit, okay, and you should be able to write on the each bit. Okay, write basically means you should be able to set or unset. You should be able to flip this. So what I'm saying is, let's suppose we'll use this a. So this is flag 1, flag 2, flag 3, flag 4, 5, 6 and 7, something like this. So this is how many flags you can use it for. But the first trick that we'll see is how to basically set up specific bit. How to set a specific bit. Okay, I have been showing you this VS Code for a while. Okay, how to set a specific bit. By setting, what I mean is, let's suppose I have this bit. I have a number a is equal 1010, something like this. Okay, now you know that there are 4 bits here. So I can use it for 4 flags. So if I want to set this bit, if I want to make this bit as 1, okay, which is unset, which is basically 0, how to do that? Okay, so that we can use a combination of these bitwise operators, because you know that these bitwise operators, they apply on a specific they apply on bit level. So how to do that is, let me show you that. The first thing is we'll create a mask. Okay, we'll create a mask. So the operation is I want to set this bit. So somehow what I can do is, if I can bring some 1 over here, and 0 over here, and then if I perform, let's suppose AND operation, say, this is one way. Okay, so then what will happen is this will be 0, but I have to preserve this also. Okay, this is, let's suppose we'll put OR operation. 0 OR is 0, 1 0 is 1, and 0 1 0 is 1, and this is 0. Now you can see that I set this bit. Okay, I was concerned with this bit. So what is the thing that I needed to? So if my number was something 1 1 0 0, and I needed to set this bit. So what I said is, you somehow get me a number which is 1 over there. Okay, and then rest it should be zeros. Okay, after that what I have to do, I'll perform OR operation between these two things. I'll call this a mask. I'll call this mask, and then I'll perform OR of this. So this is 0 1 1 and 1. So you see that I set this bit. This bit is now set. Initially it was unset. So how to do that? Okay, now you know that what will I do is, if I have a number and I want to set its any bit, let's say I want to set its nth bit. So what I'll do is, I'll perform 1 left shift by n. Okay, this is my mask. So this basically is my mask. Okay, again coming here, so what I said is, so somehow I should have a mechanism by which I can get 1 over here. So I told you that, so if I have a number say 1010, I want this bit should be set. So somehow I want a mask like this 1000. So how to get this? So what I'll do is I'll take number 1, I'll left shift it by how many bits? This is 1, 2 and 3. I'll left shift by 3 because 1 is represented like this. When I left shift it thrice, so it will become like this. Okay, so this will basically get left shifted. This is left shift twice. This is 1000. So this will be the left shift once. Basically, one will come here. Left shift twice. One will come here. This is left shift twice rather. Okay, so this is 0th bit, 1 bit, second bit. We are setting the second bit. So I have to left shift it by 2. So this is my mask now. So on the mask, what I'll do is I'll perform OR operation. Okay, that's how I'll set the bit. So this is how I can use it for flags. Let's go to VS Code and I'll show you that. Okay, let me show you this. So if you can see the code over here, I pasted some lines of code. So what I've done is the first thing is, let's suppose I have a number 5. So number 5 is written in binary like 0101. Okay, so this is the binary representation. If I can zoom it a bit more. So here if you see this, so this is the binary representation. Now I want the third bit to be set because this is a 0 first and this is second and this is the third bit. Last bit is the third bit. So here we have 0, 1, 0, 1. So this bit I want to set. So what I'll do is I'll first apply the mask. So the mask is this. So this is my mask because I am taking this 1, left shift it by the bit position, that's 3. So what I'll get is I'll basically get 1 under that 0. Okay, I'll get 1 under that 0. Okay, then I'll perform this OR operation. Okay, so if I just first print the binary of this number, print binary of 5, binary of number. Okay, and then I'll also put the binary of the result. So let's now run this code. So if you see over here, the first it was 0, 0B101. Basically, this is 3 bits. It's showing only 3 bits, but we know that it is 1010, something like this. So what if I wanted to set, and I'll clear this. So what I wanted to do is I wanted to set this bit. So what I did is I brought this 1 under it. I brought 1000, and then I performed OR operation. This bit got set. Okay, this bit got 1. So if you see it over here. So did you understand how we set the bit? Okay, now we can unset the bit also. Okay, we can unset the bit. So how to unset this bit? Okay, by unset I mean, let's suppose we have 1101. I want to unset this. Okay, I want to unset this bit at bit level. This is my number A and I want to unset this bit. So how to unset this? Somehow what I can do is, if I got 0 under here, let's say, okay, if I got somehow I got 0 under here, and if I performed AND operation, 1 and 0, okay, here if I what I'll get is, if I got 1, 1 and 1, something like this over here. Okay, my first check the goal. My goal is that somehow I should get 0 under it, so that if I perform AND operation, I'll get 0 under this. Okay, or we have one more method. So what is that one more? If this bit is 1, if I can get 1 over here and I can perform XOR, if somehow I can get 1 on this, and then if I perform XOR, then what will happen is this bit will be unset. This will become as 0. Is it clear for you guys? So what I'm saying is, I'm saying if you have to unset a bit, the two things that you can do is, one thing is, if you want to achieve it by using the AND operation, so you need to get 0 over here. Or if you want to get it done by XOR operation, you need to somehow get 1 over here, because 1 XOR 1 is 0. Okay? Is it clear? I cannot see the screen. Let me just shift the screen so that I'll see. If you, what I'll do is, so if you see, this is the operation. So I can either use AND, I can use XOR also. So the one simplest thing that I can do is, what I'll do is, I again have to create a mask, because mask is necessary. So I'll create a mask. I'll left shift again the bit. So I'll use this one, left shift the bit to the position, whatever position we have. Let's suppose this is the bit that we want to unset. Okay, first I'll get 1 over here, then I'll get zeros over here. Okay, then what I'll do is, I'll flip this. I'll flip all of these. I'll perform a NOT operation on this. So NOT of this. NOT of this will be 1, 0, 1 and 1. Okay, and then I'll perform. This is my inverted mask. So this was my mask, this is my mask, this is my inverted mask. Okay, now I can unset, I can perform the AND operation. I can perform AND between these two. 1 and 1 is 1, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. So now you saw that this bit got unset. Unset basically from 1 to 0. Okay, so what is the operation? So I have to create a mask. If you see, I have to create a mask. So how I create that mask? I'll use the 1 and left shift it by the position that I want to unset. Okay, so once I have this, so then I'll use the inverted mask. Inverted mask basically means I'll just toggle all the bits. Okay, I'll just use this inverted mask, and on this inverted mask I'll perform AND operation with the original number, whichever I have, the bit pattern which I have, bit pattern. Okay, so let's now go to the coding screen to see it. This is my VS code, and let's go there. So now let's suppose I want to set the bit. The mask is there. Okay, the only thing that I have to do is 1 and now we have to perform not of this, not of the mask rather. So mask is, then we'll perform inverted mask. Say I can perform that over here also. Not, but I need to take care of the precedence. This mask can be now. Okay, now the bit is 0 1 third bit, and this is, I want, let's suppose 0 1 second bit, because this is 0 1 0. So I want to unset this second bit, like 0 1 and 2. Okay, I want to unset that. The number I want to get is 0 0 0 1. And now let's run this code. If I run it, you can see it clearly over here. So 0b, so we had number 0 1 0 1. So we unset this bit. Okay, that is 0 0 0 1. That is basically binary 1. That's why you can see over here, this is 0b1. Is it clear how to set and unset the bits? If it is clear, that you can now use a single number for multiple flags. Okay, if you can set and unset the bit, so now you know how to set and how to unset the bit. So you can use a single number. You can use a single number for the single number as multiple flags. So for the people who have not used this flag so far, if they have less exposure to the programming, probably we'll use these very heavily once we go to the project. And all of these things, just keep in mind that we are going to make a mini project. We'll use most of these operations there. Okay. And now you saw the power of bitwise operators. I just told you how to, 4 things that we saw: how to multiply with powers of 2, and how to divide with powers of 2. Okay. I also said how to check for odd and how to check for even. And then we said how to set and unset some bits. Okay, and there are a lot more to come. Okay, probably if in the next session I would cover them in maybe next half an hour or so, but time is less. In the next session we'll cover them in the first half, and after that we'll go to code the parts of the project that we have the basics for. I'll stop the recording. If you guys have any questions, please feel free to ask.